Welcome everyone. In this video lecture, we will solve a problem based on the Mosfet small signal model and operation numerical number 2. So in this question, given an NMOS transistor H mu n CUX is given 60 microampere per volt square. Okay, this mu n CUX is given. W by L, the aspect ratio is given. Threshold voltage is given. Also, the VA, process transconductance parameter VA, is also given. So we have to find the transconductance and finite output resistance. Okay, and this one for the given bias voltage 1.5 volt, and for the bias current this we have to find out. Okay, so before that, solve this problem, I just want to write down the fundamental formula that we have to use for the calculation of transconductance. So I am writing here for NMOS. Okay, for NMOS, the transconductance formula, that is our GM, is simply mu n COX W by L VGS minus VT. Okay, and sometimes it is also written as mu n COX W by L VOV. VGS minus VT is this one. Okay, this one is one formula. In addition to that, one more formula is there, twice mu n COX W by L times of ID. Okay, what should be in this one? Or one more formula, twice ID by VOV. Okay, this is for the transconductor, and for the R naught, the finite output resistance is simply VA by ID, that you have to remember, and it is simply 1 by lambda ID. So these are the some formula that we have to know for PMOS. Okay, I am also highlighting for PMOS. Only the change you have to do, instead of this I am writing like GMP, we have to mu n, instead of mu n we have to write mu p COX W P by like LP we can write, and you have to take the modulus VOV. Okay. Similarly for R naught, mu n mu p will be, mu n is replaced with mu p. Okay, and the VOV, the overdrive voltage, is just we have to take the modulus. Okay, so in this case it should be our VA by ID. Okay, so this is the two formula, and they are the very important formula. Okay, for the NMOS and PMOS. Likewise, you can solve any problem. Okay, so now we will go for the problem. Okay, so the very first problem is for a bias voltage given, VGS is 1.5 volt is given. Okay, so we have to find the transconductance. So VGS is given, other parameter like mu n COX is also given. So I am writing 6 microampere per volt square. W by L is also given 40, and VT is also given 1 volt, and VA is given 15 volt. Okay, it is coming from the channel length modulation. Okay, for brief I just want to show you what is the VA. If we draw the ID, the drain current, and VDS curve. Okay, so our curve will be like this for different VGS minus VT. Okay, for different VGS minus VT, suppose this one for 1 volt, and I am saying this one VGS minus VT for 2 volt or 1.5 volt, or like that. So if we extend, okay, it will come and meet. If we extrapolate this, it will come and meet. This point is our VA. Okay, this one is our VA, and minus VA we can write, and it will be So basically in this case the channel length modulation means ID value. Just I want to write the formula 1 by 2 mu n cox w by l vgs minus vt in 1 plus lambda vds. When ID is 0, vds will be okay. When vds is 0, okay, in this vds, sorry, when what I am saying, when id is 0, drain current is 0, okay, then this vds equals to minus 1 by lambda. So this point you also call your va. Va point, process transfer. Okay, in data specificity it will be given. So now we have to focus on the problem. Okay, these are some basics that we have to know. So basically in this one what we can do, we have to find easily the value of id. Okay, id is known to us, then we can find the r0 value or gm. Or before that, for gm what we can write, mu n cox w by l vgs minus vt. Okay, for the transconductance transconductance formula gm, so everything is given. So it is 60 into 10 to the power minus 6 micro. I am writing like this. 40 into vgs is given 1.5 volt. 1.5 minus 1. Okay, so 2400 into 10 to the power minus 6 into 0.5. If you remove this test, it should be like this. 240. Okay, or one can write 240 into 5, what I am writing, into 10 to the power minus 3 and divided by 10 to the power 3. Why I am writing 10 to the power minus 6? 10, this will okay. Then this should be 2240, 240 into 5 into 10 to the power 3. So if we solve, it will come like this. So this way simple from how I am solving millisiemens, or one can write 1.2 milli ampere by volt. This one is our simply our gm. So this one is the calculation for gm. Okay, this one is the formula, standard formula we have written. Okay, for gm not a issue. Now for r naught, now for r naught, okay, now for r naught, okay, for r naught we have to write va is given but id is not given. So what we have to do, we have to find id. So id, so in this case we have to consider this was the saturation region, vgs minus vt whole square. For the amplifier amplification purpose, we have to take the Mosfet as a in a saturation region. Okay, clear. For the amplifier design, or for the amplifier design, the linear amplification can be obtained by considering the Mosfet in the saturation region. Okay, in the last video I also mentioned. So this one is 1 by 2 into 60 into 10 to the power minus 6, then it's w by l is 40, then 1.5 minus 1 whole square. Okay, now we have to solve. So it should be 20. So 6 into 2, 12. 1200, what I am writing, 10 to the power minus 3, 10 to the power minus 3, then 1.5. So we can write it 0.5 into 0.5. Okay, if we remove this decimal, means how I am solving, that I am showing 12. Okay, then 12 into 25 by, we can write 10 to the power 3, 10 to the power minus 3. So it should be 12 into 25, 250, 300. 300 divided by 10 to the power 3 into 10 to the power minus 3. Okay, means this should be 10 to the power 3, means 0.3 milli ampere. So now the value of id is known to us. Okay, this ID value is known to us 0.3 milliampere. So R naught will be VA is also given. This point is given 15 volt. In the question it is given 15 volt. Okay, so one can simply write 15 by 0.3 into 10 to the power minus 3. So how we will solve? Take remove this is for 3, 5. So 50 into 10 to the power 3. So R naught equals to 50 kilo ohm. Okay, so this one is the answer. ID will be 0.3, then R naught will be 50 kilo ohm by using this formula. Okay, VA by ID or 1 by lambda ID you can. Okay, and for this one we have used this drain current equation in the saturation region, because for the amplification purpose, for the linear amplification, we have to take the Mosfet in the saturation region. So this is about the first part. When this one is given, VGS is given. Okay, majorly VGS is given, and other things are also given. This one is common term when VGS. Now we have to do it for the other. Okay, means uh, in the question now bias current, now ID is given. Okay, now in the second part, in the second part in the second part ID is given 0.5 milliampere. Okay, ID is given 0.5 milliampere. Then we have to find GM and R naught. In addition to that, some other parameter like other parameter is also given. Like once again I'm writing mu and COX is 60 unit microampere per volt square. W by L is given 40. Okay, Vt is given what, how much, 1 volt. Okay, in addition to that Va is given 15 volt. Okay, so now the thing that is our missing is our VGS, because if we write GM formula, then it should be mu n COX W by L VGS minus Vt. So here VGS is unknown, so VGS we have to find. So VGS how we will find? From this ID, because drain current is given. So now again the drain current is given, this one is given. So just by writing 1 by 2 mu n COX W by L, this one is the standard formula for the drain current in the saturation region. Okay, and this ID value is given 0.5 milliampere. So I am writing simply 5 milliampere, or simply 0.5 into 10 to the power minus 3. Okay, now after that again what we can do? Okay, I am writing that down. 0.5 into 10 to the power minus 3 is given. 1 by 2 mu and COX is given 60 into 10 to the power minus 6. W by L 40 into VGS minus VT. So I am just writing like this. Okay, this should be 30. So this should be also equal 1 2 double 0 into 10 to the power minus 6 into VGS minus VT whole square. Okay, okay, now we will go for more simplification. So 0.5 milli. Okay, so now one can write 1200 as a 1.2 into 10 to the power minus 3, because 10 to the power minus 3, so 1000 will become down. So for these two one can write 1.2 into 10 to the power minus 3 VGS minus VT whole square. So this and this will cancel out. So VGS minus VT whole square is nothing but simply 0.5 by 1.2, or we can write as 5 by 12. Okay, VGS by VT will be 5 by 12. Okay, simply, or 0.416 we can. So the exact value of VGS minus VT we can calculate by squaring. Okay, so it will come around, if you solve this one, will come 1.645. Okay, no, 0.645. VGS minus VT. 0.416. If we do in calculator, it will come 0. I have already solved, so that's why I'm making it 0.645. Okay, so VGS minus VT is required. Okay, and VGS minus VT we have already calculated. VGS also we can say VGS VT plus this one. So 1 point. If we have to find VGS, it should be 0.645 plus VT. Okay, so VT is 1.645 plus 1. I am writing each and every step. So okay, this should be in volt. Okay, but our desired thing is VGS minus VT. Okay, so what we can do, so gm mu n cox is given 60 micro. Okay, w by l 40, vgs minus vt 0.64, 0.645. Okay, once again I am highlighting, means our formula is this. Okay, so vgs minus vt is required, or vgs we can say. So vgs is also we have calculated, but vgs minus vt is there. So instead of this mu and cox, w by l is this, and 0.645. Okay, so now we have to solve this one. So it should be 2400 into 10 to the minus 6 into 0.645. How I will solve this one? Means what we can write, 2.4 into 10 to the power minus 3, 0.645. Okay, because for this I am writing 10 to the power minus 3, 10,000 2.4 minus this. Okay, to 0.645. Now because maximum time we are writing gm in millisiemens or milliampere per volt. So 2.4 into 0.645, if you multiply it will come 148. Okay, millisiemens, or one can write 1.55 milliampere per volt. Okay, so now gm value we have calculated at 1.55 millisiemens also, right, or 1.55, anything, both are correct. Okay, so gm is now calculated. Now the last one thing, r naught va. Okay, by id, and id is given. So va is simply our 15 volt, and id is given 0.5 milliamperes. Milli means 10 to the power minus 3. So one can write 15 into 10 to the power minus 3, and if this decimal if we remove, this would be 150, 150 by 5, then it should be plus. Okay, so 30 into 10 to the power 3. Okay, so 30 kilo. So the gm is 1.55 milliampere per volt, and r naught value will be simply our 30 kilo. So this one is the final answer when id is given. Id is given. Okay, so like that you can solve this problem, and this problem is very simple. But the thing is that you have to remember some formula. Okay, like this gm, and it can be very easily remembered by id democrat equation, then differentiate id by del id by del vgs. Okay, for this thing I am also writing note. In note I am writing how to, means if id in saturation is given 1 by 2 mu n cox w by l vgs minus vt whole square. Now for the transconductance, okay, we have to do del id by del vgs. Okay, that you have to do. So if you differentiate this one, 1 by 2 mu n cox w by l twice vgs minus vt, and vgs is 1. Okay, differentiate twice times of vgs minus vt, and VGS coefficient is 1, so it should be 1. So this so GM formula is simply mu n COX W by L VGS minus VT, or you can write it GM W by L VOV over drive voltage. Okay, so this is all about this question. So thank you for watching this video. Okay, so we have calculated both GM and R naught value for bias voltage point 1.5 volt and IT 0.5 milliampere. So thank you for watching this video.